Have you ever downloaded a Linux ISO and skipped the signature verification? Or shared a file without encrypting or signing it? Right now, on a server you don't control, your files are sitting there, unencrypted. That PDF you emailed, readable by anyone with access. That backup in the cloud, no different. And if someone changes them, you will never know. You can't prove what you sent, you can't verify what you downloaded, unless you understand GPG. Hello everyone, welcome back to the SysGuides YouTube channel. Today, we're finally giving GPG the attention it deserves. And no, you don't need a degree in cryptography to use it. Whether you're sending sensitive files, backing up important documents, proving a file came from you, or verifying that downloaded software is legitimate, GPG has you covered. So here's what we will cover. First, a quick intro to what GPG actually is. Then we will encrypt and decrypt files using both passwords and keys. We'll learn how to digitally sign documents to prove they're from you, and how to verify files from others. Sounds good? Let's get started. So, what exactly is GPG? GPG stands for GNU Privacy Guard. It's a free open source tool that implements the OpenPGP standard, basically the same crypto standard that the original PGP software uses, but completely free and community driven. At its heart, GPG is a tool that lets you do two things: encrypt data and create digital signatures. Basically, it helps you hide secrets and prove you're really who you say you are. From these two capabilities, we get 4 practical operations: encrypt, decrypt, sign, and verify. Everything GPG does, no matter how complex, is just a combination of these 4. Let's break them down super simple. First up, encryption and decryption. Think of encryption as a way to scramble your data into complete nonsense. To anyone else, it just looks like meaningless digital noise. The words are all still there, but they don't make any sense to anyone looking at them. Decryption is simply the reverse. It's what happens when that secret message reaches the right person. They take that scrambled text and change it back into the original, readable version. So, encryption hides the information, decryption brings it back. Next up, signing and verification. Signing is not about hiding information, it's about proving something. Think of a digital signature like an old-school wax seal on an envelope. When you sign a file or an email, you're basically stamping your unique personal seal on it. It doesn't hide what's inside. The contents stay readable. Instead, it proves 2 very important things. First, that the message truly came from you, and second, that no one has opened the envelope or changed the letter inside since you sealed it. If even a single character is modified, the seal breaks. Verification is what happens on the other end. When your friend receives that message, they check the seal. If the seal is intact and matches your unique stamp, the message is verified. They know it's really from you and that not a single comma has been changed. But if the message is tampered with while it's in transit, that digital seal breaks. When your friend tries to verify it, the verification fails, clearly showing that the message has been altered. So, to put it simply, signing proves who sent it, verification proves it hasn't been tampered with. So that's GPG in theory. 4 simple operations, powerful consequences. Now let's start with the first 2, encryption and decryption. All right, just remember this. Encryption is the process of converting original data into an unreadable form. Decryption is the reverse process. It takes that unreadable data and turns it back into the original form. Now, before we encrypt anything, we need to make sure GPG is actually installed on the system. For this demo, I am using Ubuntu 24.04 LTS, but the distribution does not really matter. The commands are the same across Linux systems. So open the terminal and run the command gpg version. If GPG is installed, you will see version information displayed on the screen like this. On most modern Linux distributions, GPG is already pre-installed, so in most cases you should see this output without any issues. What you need to check here is the version number. It should show version 2. Any version starting from 2 is fine. Version 1 is outdated, so if you see that, you should upgrade. But if instead of seeing the version number, you get an error such as command not found, It means GPG is not installed on your system. In that case, run this command to install it. Now, GPG lets you encrypt files in two ways, symmetric and asymmetric. I will show you both, but before we jump into commands, let's understand what these actually mean. Symmetric and asymmetric are not individual encryption algorithms. They are broader concepts. They explain how keys are created and used in encryption, not which actual algorithm is running behind the scenes. In symmetric encryption, there is only one secret key. The same key is used to encrypt the data and to decrypt the data. To make this simple, think of it like a passphrase. When you encrypt a file, you enter a passphrase. Later, when you want to decrypt it, you must enter that exact same passphrase. The same secret is used in both directions. Now, technically, behind the scenes, GPG does not use your passphrase directly as the encryption key. It runs the passphrase through a derivation process to generate a strong cryptographic key. That derived key is what actually encrypts the file. But from your perspective, all you need to remember is this. The same passphrase is required for encryption and decryption. One key, two operations. In asymmetric encryption, there are two keys, a public key and a private key. Your private key stays with you, it never leaves your control. Your public key, on the other hand, can be shared freely. You can post it on your website, email it to people, or upload it anywhere. Anyone who wants to send you something securely uses your public key to encrypt it, and the only person who can decrypt it is you, using your private key. Two keys, two different roles. It might sound a little confusing right now, and that's perfectly fine. Once we start encrypting and decrypting real files, the difference between these two methods will make more sense. Alright, let's start with symmetric encryption first. Symmetric encryption is the simplest way to encrypt a file in GPG. There is no need to generate a key pair beforehand, so you can start encrypting files right away. I will create a simple text file called message.txt. Inside it, I'll just add a couple of lines of text that we can use for demonstration. I'm using a plain text file here just to keep things simple, but it could be any file, it doesn't make any difference. The text file has been created, containing the lines we just added. Now, let's check the type of this file using the file command. As expected, it is identified as ASCII text, which means it's just a simple text file. Now, let's encrypt this file using symmetric encryption. GPG now asks for a passphrase. This passphrase will be used to encrypt and later decrypt the file. We need to enter the same passphrase again to confirm it, and the file is now encrypted. Let's see what GPG created. As you can see, a new file with the same name but with a .gpg extension has been created. This is the encrypted version of our original file. Now, let's try to view the encrypted file. And as you can see, the contents are not readable anymore. This is encrypted data, also called ciphertext. Now let's check the type of this encrypted file. As you can see, it is identified as PGP symmetric encrypted data using AES with a 256-bit key. If you want to see more detailed information about how this file is encrypted, run this command: GPG list packets and the GPG encrypted file. I won't go through every line of this output in detail, but let's briefly look at a few important parts. Here we can see that the encryption algorithm used is AES-256, and here it shows that the file is protected with one passphrase. This section contains information about how the passphrase is converted into an encryption key. The salt is a random value that is added to the passphrase before the key is generated. This ensures that even if two people use the same passphrase, the resulting encryption keys will still be different. It also prevents attackers from using pre-computed tables, often called rainbow tables, to guess passphrases. The count indicates how many times the key derivation process is repeated. Instead of converting the passphrase into a key just once, GPG repeats the process many times. Here, the process is repeated about 65 million times, which makes brute force attacks significantly slower and harder. So the salt adds randomness and the count adds computational cost, both of which help strengthen passphrase-based encryption. This section represents the actual encrypted data packet, which contains the ciphertext produced during encryption. This section shows that the data inside the file is compressed, and algo equals 1 indicates that zip compression is used. This section describes the original file information, including the creation time, which is stored as a Unix timestamp, the original file name, and the size of the data, which in this case is 68 bytes. You can also specify your own output file name using the output option. For example, here I specify secret.dat. Now enter the passphrase. And if we check the file type, we can see that it is again identified as PGP, Symmetric Encrypted Data, using AS256. So far, the encrypted files we created are in binary format. This works perfectly when storing the file on disk. But sometimes you may want to send encrypted data through email, chat, or paste it into a document. Some systems handle plain text more reliably than raw binary data. In such cases, GPG can convert the encrypted data into a text-based format called ASCII-Armored. Here I'm using the --armor option to produce ASCII-Armored output. This will create an encrypted file in ASCII-Armored text format. As you can see, a new file with the .asc extension has been created. This is the ASCII-Armored version of the encrypted file. Now let's see what this file contains. As you can see, the encrypted data is now stored in plain text format. The message starts with begin PGP message and ends with end PGP message. Everything between these markers is the ASCII-Armored encrypted data. Because it is plain text, you can attach this file as it is, or copy the text and paste it directly into the body of an email or chat message. The recipient can either download the .asc file, or copy this text and save it into a file, and then decrypt it using GPG and the passphrase. So this is how you can encrypt a file using symmetric encryption in GPG. Next, we'll see how to decrypt the encrypted file. To decrypt a file, you can simply provide the encrypted file to the GPG command. GPG can recognize that the file contains open PGP encrypted data, and it automatically attempts to decrypt it. Now enter the same passphrase that was used during encryption. Remember, in symmetric encryption, the same key or passphrase is used for both encryption and decryption. By default, GPG restores the file using the original file name stored inside the encrypted data. Since the original file message.txt still exists, GPG is asking whether it should overwrite it. Here you can either overwrite the existing file or provide a different name for the decrypted output by pressing N. I will press N here. I will name it msg.txt. As you can see, a new file called msg.txt has been created. This is the decrypted file. If you just want to quickly view the decrypted content, you can use the --decrypt option. Instead of creating a new file, the decrypted content will be displayed directly in the terminal. You may notice that this time GPG did not ask for the passphrase again. This is because GPG agent temporarily caches the passphrase, so you don't have to enter it repeatedly within a short period of time. The passphrase is cached only temporarily, and after about 10 minutes, GPG will ask for the passphrase again. If you want to decrypt the file and save the output to a specific file, you can use the --output option along with --decrypt. Here I'm specifying restored.txt as the output file. Let's list the files in the directory again. As you can see, a new file called restored.txt has been created. If we display the contents of this file, we can see the original message has been restored. To confirm that the decrypted files are exactly the same as the original file, we can compare their SHA-256 checksums. As you can see, all three files have the same SHA-256 hash value, which means their contents are identical. This confirms that the encryption and decryption process preserved the original data exactly. So this is how symmetric encryption and decryption work in GPG. A single passphrase is used to encrypt the file, and the same passphrase is required to decrypt it. Encrypting files just for yourself works fine, but symmetric encryption becomes difficult to manage when many people are involved, because the same passphrase must be shared securely beforehand. It can also become hard to manage when you have many different passphrases for multiple encrypted files over time. And asymmetric encryption solves this problem by using something called a key pair. So before we start using asymmetric encryption in GPG, let's first understand what a key pair is. The asymmetric key pair system is one of the flagship features of GPG. In fact, key pairs, public keys, and private keys are used everywhere in modern computing for security and trust. For example, Linux distributions use key pairs to sign software packages, so your system can verify updates. Developers also use key pairs to sign software downloads. Secure boot relies on key pairs to ensure trusted operating systems are loaded. And secure websites using HTTPS also depend on public key cryptography. So even if you don't realize it, key pairs are already protecting many of the things you do on your computer every day. Because of this, it is a good habit for anyone who works with computers and wants to communicate securely to generate their own key pair. So let's start by creating our own GPG key pair, and then we'll see how it can be used for encryption, decryption, and later for signing and verification in secure communication. To create a new key pair, run the command gpg full generate key and press enter. GPG now asks what type of key we want to create. Option 1 is RSA and RSA, which uses the RSA algorithm for both signing and encryption. RSA is a widely used public key algorithm and has been around for many years. The default option here is 9, which is ECC, sign and encrypt. ECC stands for elliptic curve cryptography. It provides strong security with smaller key sizes and better performance compared to traditional RSA keys. Because of this, ECC has become the recommended modern choice for many cryptographic systems. Since option 9 is already selected as the default, I will simply press enter to accept it. Next, GPG asks which elliptic curve we want to use. These curves define the mathematical parameters used by the ECC algorithm. The default option here is 1, curve 25519, which is a modern, widely trusted curve designed for both strong security and good performance. Since this is the recommended and commonly used option, I will simply press enter to accept the default. Next, GPG asks how long this key should remain valid. Setting an expiration date is considered a good security practice. It allows keys to be rotated or replaced periodically, especially if a key is lost, compromised, or no longer needed. You can choose any period depending on your needs. For this demonstration, I will set the key to expire in 1 year, so I will type 1Y and press enter. GPG now shows the exact expiration date based on the value we entered and asked for confirmation. Since this looks correct, I will press Y and then enter to continue. GPG now asks for a user ID, which is used to identify the owner of this key. The user ID typically includes your name and email address so people can recognize who the key belongs to. It is generally a good idea to use the real name that others know you by, especially if you plan to use this key for professional communication or signing software. So enter your name here. For this demonstration, I will enter my name. Next, GPG asks for an email address. This email address becomes part of the user ID and helps others identify which key belongs to which person. It is best to use the email address you normally communicate with so people can easily recognize that the key belongs to you. For this demonstration, I will enter a dummy email address since I will not be using this key, but you should normally enter your real one. Next, GPG asks for a comment. This field is optional and can be used to add additional information about the key, such as a project name, organization, or the purpose of the key. For this demonstration, I will enter sysguides as the comment. GPG now shows a summary of the user ID we just entered. If something is incorrect, you can change the name, comment, or email address here. Since everything looks correct, I will press O for OK and then press Enter to continue. Next, GPG asks for a passphrase. This passphrase is used to protect your private key. Whenever the private key is used, for example, to decrypt a message or sign data, GPG will ask for this passphrase to unlock it. So it is important to choose a strong passphrase that you can remember. Enter the same passphrase again to confirm it. GPG has now finished generating the key pair. During this process, it created both a public key and a private key, which together form the key pair used in asymmetric encryption. The public key can be shared with others so they can send you encrypted data, while the private key remains securely stored on your system and is used to decrypt those messages. Now let's list the keys that we created. GPG stores these keys in something called a keyring. So let's first look at the public keys stored in the keyring. This line shows the public key, along with the algorithm used and the expiration date. This is the fingerprint of the key, which uniquely identifies it. This is the identity associated with the key, the name, comment, and email address we provided. And this line indicates that the key pair can also be used for encryption. Now let's look at the private key. This command shows the private key stored in the keyring. This line represents the private key. The rest of the information is similar to what we saw earlier, including the key fingerprint and the associated identity. So together, the public key and the private key form the key pair used in asymmetric encryption. We just looked at how to list the public and private keys stored in the keyring, but those commands show the keys in a summarized format. Let's now take a look at how these keys actually look. This is how the public key looks in a readable text format called ASCII-Armored. This is my public key. The public key is the one you can safely share with others so they can send you encrypted data. Now let's take a look at the private key. This is my private key. Unlike the public key, this must never be shared with anyone. This is very important. If someone gets access to your private key, they can decrypt your encrypted messages and impersonate you. I am showing this only for educational purposes so you can understand how it looks. In practice, your private key should always remain secret. You do not need to display it like this or export it, and it must never be shared with anyone. Now let's quickly see where GPG stores these keys on the system. GPG stores all key-related data inside a directory called .gnupg in your Home folder. It contains your public keys, private keys, and other configuration files used by GPG. So we've already seen how to encrypt and decrypt files using symmetric encryption, where a single passphrase, or a single key, is used for both operations. Now let's see how to do the same using a key pair, which consists of a public key and a private key. Unlike symmetric encryption, asymmetric encryption is designed for secure communication between different users. One person uses your public key to encrypt data, and only your private key can decrypt it. This is what makes it so powerful. There is no need to share a secret passphrase beforehand, which makes communication much more secure and easier to manage. Before we see how this works between two different users, let me first show you how to encrypt and decrypt a file using your own key pair. This will help you clearly understand the process. So let me clean up the files from the previous symmetric encryption examples and keep only the original message.txt file, so we can use it to demonstrate encryption and decryption, this time using a key pair. Now let's encrypt this file, message.txt, using the key pair. So I will run the command GPG, followed by --encrypt, which tells GPG to encrypt the file, then --recipient to specify whose public key should be used for encryption. Here you provide the recipient's identity, and GPG will automatically use the corresponding public key. In this case, I will provide my own email address, since I am encrypting the file using my own public key. Later, I will show you how to encrypt a message for someone else. And finally, I specify the file I want to encrypt, which is message.txt. Notice that this time, GPG did not ask for a passphrase while encrypting the file. This is because encryption is done using the public key, which does not require any passphrase. All you need to remember is one passphrase, the one that protects your private key, which is only required when decrypting. Now, let's take a look at the contents of this encrypted file. As expected, the output is unreadable and is encrypted data. Just like we saw earlier with symmetric encryption, we can also use ASCII-Armored here to generate a text-based encrypted file. So let's try that as well. Now, let's take a look at the armored file. As expected, the encrypted data is now in a regular text format, just like before. Now that we have seen how to encrypt a file using a public key, let's see how to decrypt it using the private key. I will remove the original message.txt file, so we can clearly see how GPG restores it during decryption without any overwrite warning. Now, to decrypt the file, I simply provide the encrypted file to GPG. This time, GPG asks for the passphrase. This is the passphrase we set earlier when creating the key pair. Notice the difference? With asymmetric encryption, the passphrase is required only during decryption, not during encryption. So instead of managing multiple passphrases for different files, you only need to remember one passphrase, which protects your private key. This makes it much easier to manage compared to symmetric encryption, where you need to remember a separate passphrase for each file. Now let's check the contents of the decrypted file. And as you can see, the original message has been successfully restored. So far, we've seen how to use a key pair to encrypt and decrypt a file for ourselves. But the real power of asymmetric encryption becomes clear when two different users communicate securely. So now let's take this one step further and see how this works between two people. To demonstrate this, I will use two separate systems. On the left side, I have my Ubuntu machine, and this is the same system I have been using throughout this video so far. So this is not a new setup, we are continuing from exactly where we left off. And on the right side, I have another system running Fedora with a user named Bill. You can think of these as two different users on a network, each with their own GPG setup and their own key pairs. Now, before we continue, there is one important requirement for secure communication using GPG. Both users must have GNU PG installed on their system, and both must have their own key pair already generated. On my system, we already created a key pair earlier, and on Bill's system, I have also already generated a key pair beforehand. In fact, this is something I strongly recommend. Even if you are not using GPG right now, it's a good idea to install it and generate your own key pair in advance. And if you plan to communicate securely with others, like your teammates, clients, or even friends and family, they should also have GPG installed and their own key pairs created. Because without key pairs on both sides, secure communication is not possible. Now let's take a look at both systems. On my system, if I list the keys, I can see my key pair here. And on Bill's system, if we list the keys, we can see that Bill also has his own key pair. So both systems are ready. Each one has its own keyring, and each one has its own identity. But at this point, they still don't know anything about each other, and that is what we are going to fix next. Now, let's say Bill wants to send me a secure message. For that to happen, Bill needs access to my public key. Because without my public key, he cannot encrypt anything for me. So the next step is to export my public key so I can share it with Bill. The command is GPG, followed by --armor. This option converts the key into a text-based format called ASCII-Armored, instead of the default binary format. It's not strictly required, but it is generally recommended when you plan to share keys between users because it's human readable, easier to handle, and works reliably across different systems and communication methods. Next is --output, where you specify the file name. I will name it my_pub.asc, but you can name it anything. Just make sure it clearly indicates that it contains a public key. And then --export, which tells GPG to export the public key. In this case, it's mine, so I will enter my email address. Now, if I list the files, you can see the public key file has been created. And if I display its contents, this is what the public key looks like in ASCII-Armored format. Now, I need to send this public key to Bill. In a real-world scenario, this could be done in many ways. You could send it over email, share it through a messaging app, copy it using a USB drive, or even host it on a website for others to download. For this demonstration, however, I will use Secure Copy to transfer the file to Bill's computer, since it makes transferring files between two virtual machines easy. The method itself is not important here. What matters is that your public key must somehow reach the other person. To do that, I need Bill's system IP address. So this is the IP address of Bill's computer. I will copy it and switch back to my system. Now I will use the scp command to send the public key file to Bill. The command is scp, followed by the file name, the file I want to send, in this case my public key, then Bill's username, the @ symbol, and his IP address. And finally, the destination path on his system. Here, I am telling scp to copy the file into Bill's documents directory inside his home folder, and Bill's user account password. And my public key has now been successfully transferred to Bill's computer. Now, in order for Bill to send me an encrypted message, he needs to import my public key into his keyring, because without my public key in his keyring, he cannot encrypt anything for me. So Bill runs the GPG import command to add my public key to his keyring. Now, if we list the keys on Bill's system, you can see that my public key has been successfully imported. The first key here belongs to Bill, and the second key is my public key, which we just added. So now Bill's system has both keys, his own key, and my public key. Now, notice this label here. It says unknown. This means that Bill's system does not yet trust my public key, even though the key has been imported. Bill has not verified that this key actually belongs to me. Now, technically, Bill can still use this public key to send me an encrypted message, but GPG will show a warning every time saying that there is no assurance that this key actually belongs to me and asking if you still want to use it anyway. So to avoid seeing this warning every time, we need to tell GPG how much we trust this public key. And to do that, we run this command, GPG --edit key, and then my email address. Since we are editing my public key, we need to specify my email address here. After pressing enter, GPG opens an interactive mode for this key. Now, to tell GPG how much I trust this key, I will type trust and press enter. GPG now shows a list of trust levels. These options are fairly self-explanatory, so you can choose based on your judgment. In most cases, you will be deciding between full trust and ultimate trust, depending on how much you trust the person behind the key. For this demonstration, since I completely trust this key, I will choose option 5, Ultimate Trust, and press enter. Now, I will confirm my choice by pressing Y, and then type quit to exit this interactive mode and save the changes. Now, if we list the keys again, you can see that the trust level has changed. Earlier, this was marked as unknown, but now it shows as ultimate. This means Bill's system now fully trusts my public key, so now GPG will no longer show warnings when using this key. Now Bill is ready to send me a secure message. So first, he creates a simple text file. And types a short secret message into it. Now, to send this securely, Bill needs to encrypt it using my public key. So I run the command, GPG, followed by --encrypt, then --recipient, and this time, my email address here. And finally, the file name. This tells GPG to encrypt the file using my public key. No passphrase is required here. Now, if we list the files again, you can see a new encrypted file has been created. Now let us see what happens if Bill tries to decrypt the file he just encrypted. And it fails. Even though Bill created this message, he still cannot decrypt it, because the file was encrypted using my public key, which means only my private key can decrypt it. So no one else, not even Bill, who created the message, can read it. Only the owner of the corresponding private key, which is me in this case, can decrypt and access the original message. This is what makes asymmetric encryption so powerful. You can safely share your public key with anyone and be confident that only you can decrypt data that was encrypted for you. And this also shows why it is extremely important to protect your private key and never share it with anyone. Now let us continue with our example. Bill now has to send this encrypted file to me. So I will use the same SCP method as before to transfer the file from Bill's system to my system. Now, back on my system, I have received the encrypted file. Now I will decrypt it. I enter my passphrase. The file is decrypted. Now, if we list the files, you can see the original file has been restored. And if I open it, I can now clearly read the message Bill sent to me. So the message has been successfully decrypted. Now, what if I want to send a secure message to Bill? For that, I need Bill's public key. So I request Bill to share his public key with me so I can also communicate securely with him. And now Bill exports his public key. Instead of using SCP this time, let us assume Bill sends his ASCII-Armored public key through email, copying it into the message body. And when I receive the email, I copy the public key from the message body and paste it into a file on my system. Next, I import Bill's public key into my keyring. And set the trust level, just like before. Once that is done, I create a message to send to Bill. And I encrypt the message using Bill's public key in ASCII-Armored format so it can be easily shared through email or messaging. And Bill copies the message and saves it to a file on his system. Now Bill decrypts it using his private key. Here, GPG is asking for the passphrase, this time using a graphical window. This is the default behavior on most systems with a graphical environment. Earlier, I had configured it to ask in the terminal for convenience, but on most systems you will usually see a window like this. The message has been successfully decrypted. Now, if we list the files and display the contents of the decrypted file, this is the message I sent. And this completes secure two-way communication using GPG. Alright, so far we have covered how to encrypt and decrypt data using GPG, both using a passphrase and using key pairs. We also saw how to share public keys, set trust, and securely communicate between two users. At this point, you already have a solid understanding of how encryption and decryption work in GPG, which is the most important part. Now let us move on to signing and verification. This part is much shorter, but it is equally important for ensuring authenticity and trust. Until now, we have been focusing on keeping data secret, making sure only the intended person can read it. But in many real-world situations, not all data needs to be secret. You may want to send it as plain data, but still prove who it came from and ensure it has not been tampered with. And that is exactly what signing and verification solve. So I will continue using the same setup as before. I will sign the file on my system, and on the other side, Bill will verify that signature. I'll be using the same text file, message.txt, as an example for both signing and verification, but this could be any type of file, like a PDF, a document, a spreadsheet, or anything else. I'm just using a simple text file to keep things easy to follow. Now, in GPG, signing can be done in two ways, attached and detached. In an attached signature, the signature is combined with the file itself, so everything stays in a single file. In a detached signature, however, the signature is stored separately as its own file. So let us start with the attached signature first. To sign a file with an attached signature, run the command gpg --sign followed by the file name, in this case message.txt. Now you will be asked to enter your private key passphrase. Notice something different here? Earlier, when I encrypted a file for Bill, I did not have to enter my passphrase. It was Bill's responsibility to use his private key to decrypt and read the message I sent. But now, I am being asked for it. Why? Because this time, I am the one creating the signature. So I need to prove that this file was created by me, so I use my private key to sign it. And to use my private key, I have to unlock it using my passphrase. And that is it. The file has now been signed. Now, if I list the files, you can see a new file has been created with a .gpg extension. This file contains both the original data and the signature together in a single file. So you only need to send this one file to anyone, and they can verify that it was signed by me. Now, I will send this signed file to Bill using the scp command. So before Bill verifies the signature, let us quickly compare when a passphrase is required. In encryption, the sender uses the receiver's public key, so no passphrase is needed while encrypting. The receiver then uses their private key and enters their passphrase to decrypt the data. But in signing, it is the opposite. The sender uses their own private key, so a passphrase is required while signing. And the receiver simply uses the sender's public key to verify the signature without any passphrase. Now, Bill will verify the signature. This is the output GPG gives for verification. As you can see here, it says good signature, which confirms that the file has not been changed since I signed it. And if you look at the signer identity, it is mine, which shows that the file was actually signed by me. This is powerful. It means Bill can trust both the file and the sender without ever contacting me directly. Now, to view the content of the file, I will use the command GPG-decrypt. At first, this might seem a little confusing. Why use the decrypt option when this file is only signed, not encrypted? But in GPG, decrypt is a generic option that is used to process both encrypted and signed files. So in this case, it will display the content and also verify the signature in the terminal output. And then I provide the signed file message.txt.gpg. As you can see, the original message is displayed here. And right below that, GPG also verifies the signature and shows that it is valid. So in a single step, we can view the content and verify the signature all in one file, since this is an attached signature. And what if you want to extract the message? You can simply run GPG on the signed file. This will extract the original content and also verify the signature. Now, if I list the files, you can see that the original file, message.txt, has been created. And if I open it, you can see the original content has been restored. What you just saw was signing a file with an attached signature in binary format. GPG also provides a way to create an attached signature in a readable text format using ASCII, similar to the ARMOR option we used during encryption. Unlike the previous method, the content remains readable, which makes it useful for text-based messages such as emails. So let us see how it works. To sign a file in a readable format, use the command GPG --clear sign, followed by the file you want to sign. Enter your private key passphrase, and that is it. The file has now been signed. Now, if I list the files, you can see a new file has been created with a .asc extension, and if I open it, you can see the content is still readable. This marks the beginning of a clear signed message. This shows the hash algorithm used for the signature. This is the original message kept in plain text. And below that is the actual digital signature. And since everything here is readable, you can copy and paste this directly into an email or any messaging platform. For this demo, I will use SCP to transfer the signed file to Bill. Now Bill will verify the clear signed message. As you can see, GPG verifies the signature and shows that it is valid. But what happens if someone modifies the message? So let me make a small change to this file. I will just remove a single character here, a comma, and then save the file. Now let us verify it again. And as you can see, the verification fails. It shows a bad signature. This means the file has been modified after it was signed. Even a tiny change, like removing a single character, completely breaks the signature. This is what ensures the integrity of the data. Now I will restore the original content. Now, if I verify it again, you can see it shows a good signature again. This confirms that the signature only works when the content remains exactly the same. And if you want to extract the message, you can simply use GPG on the signed file, just like we did earlier. So far, we have seen how attached signatures work in both binary and readable formats. Now let us move on to detached signatures, where the signature is stored separately from the original file. Let me first clean up the previous files before we continue. To create a detached signature, use the command GPG -- detach sign, followed by the file you want to sign. Enter your private key passphrase, and that is it. The signature has been created. Unlike the previous methods, this does not modify the original file. Instead, it creates a separate signature file while keeping the original file unchanged. This is what makes detached signatures very useful in practice. And when you want to share it, you need to send both the original file and its signature file. So I will send both files to Bill. Now Bill will verify the detached signature. Here, we provide two files, first the signature file, and then the original file. And as you can see, GPG verifies the signature and shows that it is valid. Now let us see what happens if I modify the file when using a detached signature. As you can see, it catches the change and reports a bad signature. This shows that detached signatures provide the same level of protection. Any modification is immediately detected. Now, I will restore the original content, and once restored, the good signature is back. Just like we saw earlier, we can also make the detached signature readable using ASCII-Armored format. So let us see how that works in our final example of signing and verification. To create an ASCII-Armored detached signature, use the command GPG -- This option makes the output readable as text, then -- detach sign, followed by the file you want to sign. Enter your private key passphrase, and that is it. The signature has been created in a readable format. Now, if I list the files, you can see a new detached signature file has been created with a .asc extension. And if I open it, you can see the signature is now in a readable format. This makes it much easier to share and verify the signature across different systems. Now I will send both the original file and the new ASCII-Armored signature file to Bill. And when Bill verifies the file, It shows good signature. And with that, we have completed signing and verification using GPG. We have seen how to ensure that a file has not been modified and that it truly comes from the expected sender. Alright, in this video, we covered how to encrypt and decrypt data using GPG and how to sign and verify it. Encryption keeps your data private, and signing ensures it is authentic and unchanged. And with that, this brings us to the end of the video. Thank you for sticking with me till the end. I hope this was clear and helpful. Let me know your thoughts in the comments. In the upcoming video, I will show how to use GPG with Thunderbird email so you can securely exchange encrypted messages with others. Until then, take care, and I will see you in the next one.